start recording. And the first thing I want to do is I do want to play. This is a slightly different. This is a different video than the clip I put out on Canvas. It is put out by the Metal Powder Federation, so it does tend to have a little bit of the powder metallurgy is going to save the world. But I think it does give us a little bit of a nice overview of the process. Rather than stopping it and starting it quite a bit, I am going to let it go. It is not necessarily new in terms of some of the, like you may notice that some of the products might look a little outdated, but the process itself is quite nice. So I'm going to go ahead and share my screen, and then I also have to make sure that I include computer sound. So here we go. Let me get this large and start. So there's the dramatic music. Yeah, if you want to turn the lights off, go ahead and do that. Just turn this top one off.
It is an industry whose roots predate recorded history, yet is marked by constant innovation.
You can lower them, is that working?
An industry that will touch nearly every aspect of our lives today.
Okay, get ready for the dramatic climax.
And help to shape our tomorrows. Powder metallurgy. An industry on the rise.
So these are just different products where we would see powder metal parts. Or wondered where Wonder Bread got its iron.
Whether you realize it or not,
The
results of PM technology are all around you. Why are so many product makers turning to powder metallurgy for creative solutions?
Product designers can very easily create unusual designs which are unavailable by any other process.
You can achieve alloy compositions and structural uniformity totally unobtainable by other methods.
Metal powder allows you to make high-volume parts without the kind of waste that you normally have with other processes.
We can design very complex shapes, and that gives us a better performing component than we would normally get with any other manufacturing method.
The sound of steel. That's what professional guitar players want from their instruments. And that's what they get with the Kahler Tremolo. These are precision-crafted devices with 20 PM steel parts. Kahler found that the only practical way to get the quality they demand is by turning to powder metallurgy.
So that's the pressing. So you can kind of see how fast the process is. And it's lovely that it's set to music. So there's the, yeah.
Powder metallurgy, or PM, is a process in which metal particles are compressed into a desired shape and then heated to a high temperature so that the particles fuse together to form a durable finished part. Seemingly a simple process, yet one that opens doors to vast possibilities. And the key to it all is metal powders. Although there are several ways to manufacture metal powders, most are created by a process called atomization. Raw materials are carefully pre-selected and then melted in an electric arc furnace. When the molten metal reaches the proper temperature and chemistry, It is transferred to an atomization chamber. Here, a stream of molten metal is intercepted by high-pressure jets of either water or gas, which break it up into droplets. Each step in the process is stringently controlled and monitored to assure the highest quality, purity, and uniformity. After a series of finishing operations, the result is a highly engineered material with very defined properties: metal powder. Particles can be created in sizes ranging from as coarse as grains of salt to as fine as baby powder, and in a wide variety of shapes and compositions. Nearly every metal known to man is available in powder form. Everything from basic elements like iron and copper to extremely sophisticated compositions such as superalloys.
I like the thought of being able to make alloys that you can't make in other ways. Alloys with unique properties that you just can't get using other things.
This unique ability to control chemical, physical, and metallurgical characteristics allows PM to custom tailor the exact properties required for the intended end use. Metal powders are essential ingredients in a broad spectrum of non-structural products. However, most powders are destined for the manufacture of high-quality structural components. Powders are selected and blended to achieve desired properties, then fed into a die, where they are compacted under high pressure at room temperature. The resulting form has the shape and size of the finished part and is strong enough to be handled. It is then heated or sintered in a protective atmosphere furnace. Here, the particles are metallurgically bonded together at a temperature below the melting point of the base metal. PM's solid-state consolidation technique makes it the most viable way to work with high melting point refractory metals, such as tungsten and tantalum. But the versatility of PM extends to more than just
Look at all
materials.
these parts and just the shape of these.
With PM, you can produce intricate shapes that would be difficult to achieve using traditional metal forming methods. And that means extraordinary design flexibility.
The reason we used powdered metal in this new product was because there were some small, complex, highly loaded parts that really needed to be made out of metal, and due to their complexity, powdered metal was the only economical manufacturing method.
PM can make many components economically without any sacrifice in the integrity of properties and performance.
And since
Look at
PM
that part.
produces net or near net shapes, there are significant savings in scrap loss, labor, time, and energy compared to other metal forming processes. PM parts are dimensionally accurate and can be consistently reproduced, so the process is ideally suited for moderate to high volume production. State-of-the-art manufacturing equipment coupled with strict adherence to quality control standards
This is a coordinate
assures
measuring
that PM
machine,
parts
so
are second to none.
gives us very
As
accurate
a product
measurement.
designer, I feel my products
Okay.
are only as good
Yeah, now we're
as the
just getting
parts
in.
going
Now
into
we're
that
just
product.
getting into the a little bit more of the saves the world. But I like a fair amount of that particular video because, well, one, the music's kind of fun, but we also you also get an idea of the process itself, so you can sort of see how fast it is. It is a fast process. I also like that there's it gives you a lot of the pictures of the process itself, or not the process, well, the process, but also the parts. So you'll notice that you can get a lot of complexity on there. The other thing that I did want to just kind of mention is talk about sound. And so one of the things that we did talk about yesterday, or like that we talked about, is we looked at the concept that the density is going to vary with powder metallurgy parts, that we always get some porosity, and that the amount of porosity that we get, we can vary it. And today, one of the things that we're going to talk about is how do we kind of compensate for that. Well, when it comes to porosity, the good is we can do a filter. We can make it a certain size if we want for good bonding. We can also make it a certain size if we want to put oil in. So we can kind of have these parts that carry their own lubricant. The bad is reduced strength, reduced ductility, reduced toughness. A neutral is reduced thermal conductivity, but we also see that some of those elastic and sound properties are different as well. So one of the things that one of the reasons why the PM parts might be attractive in the musical instruments is that, and I think you might have done something about, or in instrumentation, where you looked at different materials and their sound. So you can have some control over the sound properties by the porosity. And so I just thought that was kind of an interesting thing as well. The last that I want to just sort of look at or talk about is that we did have that concept of superalloy. Okay, I just learned that I can change the color of my pen by just hovering over in the lower left-hand corner. So, did you notice that little jar of superalloy in terms of the powder? Does anybody remember? We might have talked about superalloys in 322, but maybe not. Has anybody heard of superalloy? Yeah, kind of like the name. So a superalloy, this is going to be a complex nickel-based alloy. And by complex, we have over 10 alloying elements. So it's a nickel-based alloy that is used in high temperature, high stress applications. Whenever I think about high temperature, high stress applications, I think of jet engines and especially jet engines for the military, for the fighters. So one of the most challenging environments is going to be a jet engine on a fighter because you need high performance and low weight. So these superalloys are very complex. And you're like, okay, where are you going with this? So one of the things we know or we realize is diffusion is slower with more alloying elements. And so also kind of think about this. So we know that with solidification, we have coring. Does anyone remember what coring is? Fine. So with solidification, we have coring. Anybody? Adam, you look like you're ready to answer the question. Okay, yes. So we have coring this is that compositional gradient. And you might not remember, very good, I'm excited. But the compositional gradient, remember, it's from the center of the dendrite to out like between the dendrites. Okay, What controls dendrite size? Do you remember that? Anybody online as well? Jason. Solidification time, right. And what kind of solidification time do we have in atomization? Would atomization be fast or slow solidification time? I'll come over here. So we have our stream of molten metal, and we're blasting it with air or water. So what does the blasting of the air or water do to the stream of the molten metal? It's going to break it up. What's the volume over surface area of what's formed? Is it high or low? Michael, you're thinking, I like that. Online, what kind of volume over surface area do we have when we break up a stream into small particles? Like,
it's low. It's
going to be really low. Like small particles have a lot of surface area for their volume. Plus, we're really having conditions with very high heat transfer. So powder metallurgy, atomization, is extremely fast solidification. So like those particles, those droplets are solid by the time they reach the ground. So for atomization, we have very fast cooling, so very small dendrites, which means we can homogenize. And homogenization is where we allow the process to, where we allow the composition to become equal. So in the video, when they talk about you can only, there's certain alloys, the only way you can make them is with powder metallurgy. It comes back to the only way you can get the composition of the material to have any sort of uniformity is with powder metallurgy. So it goes, again, we're going back to cooling rate, dendrite size, and so forth. By the way, this is just something that I like to try to tie into what we talked about last term. So sometimes there are kind of some very specialized applications. So, well, thank you for going along with this. I hope you kind of can see the connection on here. But let's move into, again, kind of quickly going over some of what we talked about yesterday. Again, we're going to be kind of thinking about shapes of the parts. What are some of the design features? What are some of the strengths and weaknesses as well? So we're not going to go over everything, but again, let's just quickly review the 4 basic steps. Powder production. We've now seen atomization. That's the most common. Our blending and mixing, again, different powders. And then the processing aids. So this would be, again, binders, lubricants. These will be removed. So these are removed in sintering. Compaction, which we saw was a relatively fast process. And then the sintering operation, which is the high temperature operation to create bonds that we also talked about yesterday. Okay, so I'm just going to kind of zip through this. just sort of highlighting what the green compact looked like. And you could see what it looked like on the video as well. This concept that, again, because the powder does not transmit the pressure well, and a pressure gradient exists, so the density gradient is going to exist as well. And again, density versus compacting pressure, and then properties versus density, and then our. So here I'm going to just sort of make a statement. I'm going to say our green density sort of controls the final density, and the final density controls properties. And so we know that pressure controls the green density. So this is sort of that sequence in terms of pressure is important in the green density controls the final density, and here we can see that the density of our part is related to the strength. So green density is more important in final strength than green strength, because in powder metallurgy, that density becomes important. Okay. And we just talked about the isostatic pressing. We looked a little bit at sintering. Again, the temperature, the time, the atmosphere. They also talked about that. I would also encourage you to watch the video clip that's on Canvas. I like to see these processes. That video clip covers a little bit different take on this. So I think that it actually nicely talks about some of the atmospheres. We talked about the 3 stages, the importance of these, and where we left off is density. Okay, so as we will notice that we do have some porosity in conventional powder metallurgy parts. In the video we just saw where it talked about, well, you can get good properties. You can get good properties with a PM part. If you're looking at the strength of a powder metallurgy part compared to a wrought part, it's not going to be as good. So we do have to realize that the porosity is going to influence some properties. We also, again, we can control the porosity, and so there's some really good things with that. Right, so here we can make filters and pores. So now what we want to look at is minimizing the negative consequences with secondary operations. So notice up here I have the word conventional powder metallurgy parts. This means we've gone through the sintering operation. Now, when it comes to the powder metallurgy, well, we have a few options. So So we have porosity. We can fill the porosity. Well, if we fill the porosity, we're going to help ourselves out a little bit. So if I infiltrate, infiltration, I fill the porosity with a metal. So, and what happens is we increase strength, ductility, therefore toughness, and we also would see an increase in conductivity. Okay, so a lot of times we might hear, for instance, copper steel PM parts. So this is going to be, so we have a steel part with copper infiltrated on there. So I don't know if in this video they talked about copper steel PM parts or it's in the one on Canvas, but you might hear that. How the infiltration is done is you would either dip the part in a vat of copper, or you would put copper sheet, very, very thin copper sheet, maybe even call it copper film, on the surface of the part, put the part in the furnace, the copper melts, and then capillary action pulls it into the pores. So again, infiltration is a very common way to fill the porosity with metal. And again, we just are helping some of those other properties. We also have impregnation, and here is where we fill with a liquid or polymer. And this could be to produce self-lubricating parts. So we would say that we could impregnate the part with oil, and that's kind of interesting. We know that when a part is in use and there's friction, it's going to heat up, it's going to expand, so those pores will expand. The oil or the lubricant kind of comes out, helps things go. It cools down, the pores get smaller, and then capillary action pulls that back in. So those self-lubricating parts are really kind of cool because they kind of carry their own lubricant with it. The other thing that we might look at for impregnation is with a polymer is we might look at to fill with a polymer to minimize corrosion. Because if you remember that we talked about increased porosity has increased corrosion. And so the part here on the left, this, you can kind of see some of the corrosion around here. The one on the right has been impregnated, and you can see that there's significantly less corrosion. And so these are sample parts by a company that does do this. So again, we can fill the porosity. The one that is really used quite a bit in connecting rods is powder metallurgy forging. And in powder metallurgy forging, we can combine the two parts, the two processes, and get the best of it. So when you hear forging, what comes to your mind? If I say forging is great because, what would you put in that blank? I could set it to the lattice forging music. It would be the like mechanical properties. That's what comes to my mind. When we talk about forging, we can get that grain flow, that fiber formation. So for powder metallurgy forging, we get the mechanical properties of forging. You know, porosity, we get that good grain structure. But with forging, there's a fair amount of waste. If you think about that hammer for the manure spreader that we had showed in the lab, there's a fair amount of waste. When we think about powder metallurgy, we think of near net shape, very little waste. So powder metallurgy forging is a combination of those two. So we use powder metallurgy to obtain a preform. So we're one press hit from our final shape, and then we hot forge to the desired shape with our metal flow and density. So powder metallurgy forging gives us the kind of I don't want to say the waste of powder metallurgy with the mechanical properties of forging. And so when you think about our good old connecting rods, these are often powder metallurgy forged. Unfortunately, it has closed, but Chrysler had a plant down in Kenosha that did powder metallurgy forging of their connecting rods and some of their other parts as well. It was very automated. You know, a lot of the powder metallurgy is much more automated or can be automated compared to standard forging. So you also have not only less material waste, you have your cycle times are higher, your cycle times are lower, and your labor costs are lower as well. Again, here is another part. You'll notice that the bottom, this is powder metallurgy forged, and you're actually also creating the teeth directly. Oftentimes in standard forging, the teeth are machined in. The top kind of gives us an idea of the weight. So again, powder metallurgy forging is a really good process when you need those really good mechanical properties. Okay, we're doing pretty good on time. So if we think about design for powder metallurgy, and certainly we need to think about the process. So I always like to kind of think about, okay, we have the die cavity, we have to fill the die. So powder has to be able to flow. We're pressing. So we need to make sure that the shape allows for pressing. Now, draft could be kind of an issue there. Straight sides work very well with this. We also need to be able to eject the part as well. And then we have sort of features in the pressing direction versus perpendicular to the pressing direction, and then undercut. So holes and features should be in the pressing direction. Again, all of those parts that I showed you, you can see that the pressing direction is where we have all the good features. That one part that I said, look at all that detail, that's all in the pressing direction. Very easy to do. If you need to do something perpendicular to the pressing direction, oftentimes you would machine that when it's in the green state. When I worked in the diamond making business, our tooling was was made by powder metallurgy, and there was some shaping that needed to be done that we couldn't press it in, and we would do some machining of the part in its green state prior to sintering. There's some challenges with that. Okay, again, low height to width is preferred, and this is because of that pressure density. Indented is preferred to raised. So we would rather have any features indented. Powder metallurgy often has been a process that's been taking up market share. So somebody has a casting and now they want to look at powder metallurgy. So if you have design features, identification features that are raised in your part, it's much easier if you can have it indented. And if it's the same, you might as well go for there. Really thin sections and walls are a problem. Some of that is for filling, some of that is for pressing. As with everything else, small steps rather than large steps. Avoid abrupt transition. And then having what we call a true radius is an issue. So we prefer for anything symmetrical or anything spherical to end on a flat. Okay, so just a few kind of overall design considerations. And here we have some kind of good versus bad. Again, sharp, we don't like sharp corners. We don't like sharp corners. We have a few examples of that. Again, we prefer not having a sharp corner. C is one that's kind of interesting. Again, this particular feature is not in the pressing direction, so this would have to be machined. If we have it here, we could actually mold it. So here's where that direction of the pressing, and then here is where we sort of end in a flat. Again, this thin section would be challenging to get metal to flow into that and to press it. It's a little bit better if we could have a thicker flange. And then again, kind of ending up here versus this more flat area. So we can't necessarily cover everything about the design of powder metallurgy. We do, again, kind of think about the metal flowing and the die. There are some really great aspects to powder metallurgy. Minimum waste. So we can press and sinter, in some cases without any finishing, some really complex shapes. And some of the parts I have kind of show that. If we want, we can produce a specified porosity. So that's kind of cool. We can get very complex features with some limitations. Different materials can be mixed, so we can get that copper and graphite if we want. And then it's the only method for some materials, and that would be some of those super alloys where we need the cooling rate of the powder in order to get the properties. There are some limitations. So our tools and equipment costs, these tend to be in the medium to high. So the video talked about this process is good for medium to high quantity production. And that's the case. So this is not, powder metallurgy is not a good process if you're making a very small quantity. So we also do have some shape limitations, and there's a higher, the starting material is a higher cost because we do have to make the atomization. You know, we do have to make the powder. There are some challenges with handling powder, but I think these three limitations for the choice of the process are good. Okay. This is the last slide where we kind of can compare, you know, casting to powder metallurgy. I'm just going to leave this up and transition to talking about our exam. Okay, so David. So I'm just going to go ahead and hand back the exam to people who are here. Okay, Jason, Darian, John, Jacob, Michael, Adam. Okay, Isaac, yours is a different exam. Okay, so okay, so again, we can kind of see that, you know, for powder metallurgy, most of the advantages of powder metallurgy compared to the other processes are related to low waste. And then we see that the advantages of these processes are either going to be in machining, its flexibility, casting, it's going to be quantity and some shape flexibility, and then forging, it's that mechanical properties. Okay. So let's look at the exam and quickly go over it. Grades were overall really nice on the exam. So again, forging and casting, that composition question, cast alloys tend to be closer to the eutectic. Wrought alloys tend to be closer to the base metal. Major advantage of forging over casting, mechanical properties. Casting over forging, it could be quantity or shape. We can do more complex shapes with casting. We can do more, we can easily do one or small number with some processes. Okay. The water valve was cast. We actually saw a cast water valve in the lab. It has an internal cavity and strength is not needed. The forging is the wrench. Again, we saw a wrench upstairs in the science building. The shape is conducive. It's a relatively simple shape. It has a high V over A, and it needs good mechanical properties. Every so often, somebody also tells me the word forged is often written on it. So yeah, I was kind of looking for those, again, taking the part to the process. Here, our CCD is, I'll do this. This is the circumscribing circle diameter. And this is the smallest diameter to fit the shape. So A and B. So A and B have the same shape, or I'm sorry, they have the same overall dimension, so they would have the same CCD. Shape factor, this is going to be perimeter to area, and it's going to be B because B has the most kind of contact area. And then if these are on the same press, we know that the pressure is related to the natural log of R, and R, the extrusion ratio, is area of the billet divided by area of the extrusion. And so R is area of billet divided by area of extruded product. And the area of C is significantly smaller than that of A and B. So if we started with the same billet, the extrusion ratio would be the highest. Okay, and those were questions. Some of that, if you remember, also came from the reading assignment. Okay. Flash is the metal thin. A core is used to create internal cavities. Ingot. Stringers, although if you said fibers, that was good too. And a chill is used to locally increase the thermal conductivity. Okay. So here we have just sort of a question. We have a situation. We have gold, 10 good intricate detail, and 2 grams. So really we're looking at what I was hoping is that you would process by process say, oh, die casting, good on surface, detail, mass. If you don't happen to know that the melting temperature of gold is about that of copper, I wasn't, it occurred to me that you might not know that, but just to kind of consider that. So the material would be fine, but die casting 10 is ridiculous for the cost of the tooling. Green sand, good on quantity. It's okay on the mass. We generally don't use precious metals because of the waste that's involved, and we cannot get the detail or the service or the surface. Investment is good on everything, and jewelry often is made that way. We can hand carve those or rapid prototype those pieces. Lost foam. Lost foam, the quantity is not great because we need molds to make the patterns. The surface isn't going to be great. We could do the material. We could do the math. So I was really just sort of, looking for combining process to there. So the best process would be investment. Okay. 3 stages. Thermal, liquid, solidification. This would be the riser. Thermal contraction of the solid. This would be the allowance. We make the part bigger. Draft, it's a taper on the side to get the part out of the mold or the pattern out of the mold. So lost foam and extrusion do not need draft. Forging, if you remember, has the most draft. So forging has more draft. If I had investment casting up here, that process also does not need draft. Okay, how am I doing on time here? So, we have a situation. Yes, CP and CPK are equal and large. So it's a good application for the process because CP and CPK are large. Now, how's the process running? Well, we have 6 in a row increasing and 1 on upper control limit. So likely a change has occurred. So check process. Have we made bad parts? Probably no, because our CP and CPK are so large. Even though we're going outside the control limits, we're still probably in spec. So that's what I was kind of looking for this, to recognize we have a trend. Even if you didn't recognize the trend, a point on the control limit should be a flag that something's likely to have changed and relating back to CP and CPK. Okay. Oh, here's the last. Okay, so here we go. Gas porosity, deoxidizing, thermal modulus, ratio of casting volume, tolerance, extrusion, process, manufacturing triangle. And I don't know, I was intrigued by what people asked me on the last question. So, you know, some nice questions there. Okay, add up your points, make sure that I didn't like mess anything up. We are going to be starting machining on Monday, and there is a reading assignment due. Thank you for staying an extra couple minutes. I hope everyone has a very good weekend. And again, I'm so glad my system worked today. If there are any questions, I'll answer them. If not, have a great weekend.